All right, today we're talking about ridge regression and how it can be used. Now remember what I told you last time about ridge regression. Ridge regression is not something where you actually get numbers that you can use, like parameter estimates. Some people try to use it that way, but in my particular view, that's not correct. The best thing to do is to get a good, say, ordinary least squares or generalized least squares model that works well and use it. So why am I teaching you ridge regression anyway if you're not going to use it, if you're not going to use the numbers? Some people do, but I don't think it's appropriate, but I'll explain why when we get to each part of it. But ridge regression is one of those really good things you need to know and to use, because it can tell you if there is a problem. And multicollinearity is a problem that can really throw the estimates off. You've already seen the example that I gave last time or last week when we showed that with a lot of interaction terms, the t-tests all crumble. And then you also saw that in addition to the parameter estimates having bad t-tests, the parameter estimates themselves may not have been good. Meaning, if you don't have good solid t-tests, do you really have a good reason to believe that the parameter estimates themselves are okay? So we want some way to be able to say, are these numbers okay? Meaning there's going to be some level of multicollinearity in every model you ever have, ever. The question is it going to be so bad that it's causing a problem? So sometimes there can be a problem, sometimes there's not a problem. You have to be able to tell the difference. And ridge regression is one of those things that is perfect. It actually tells you if your estimates are stable. So what we're going to do today is simply go through the ridge regression part of the code. We've already gone through the other part of the code, dealing with the tolerance and the variance inflation factors, diagnostics for multicollinearity, and the correlation coefficient. Now we're going to go through this part at the bottom where we deal with the ridge regression. So on your computers right now, you've already installed the car package. But if you have not yet installed the MASS package, M-A-S-S, please do that right this very second, right now, on your computers, M-A-S-S. Because in addition, the car factor is what you needed for the VIF things, but for the ridge regression, you need the M-A-S-S. So please do that as I'm speaking right now, if you haven't done that. And now I'm going to run the entire thing. So that's what I'd like you to do. And again, if you're using RStudio, get rid of this Windows parenthesis command, and then just run the whole thing. And then let's actually look at what we actually get. So let's first run it, and then I'll come back to this page and explain it. And we don't need the earlier plots. These ones here just have regression diagnostic stuff, so I'm going to click those away. We are going to use these ridge regression plots. And this last thing I need to hit the enter button to get the answer for us. And all right, so we've got a bunch of stuff. Now let's go back to the actual code. So what I'm interested in now is just that you have actually got it to run. And if you have the MASS thing installed and the car thing installed, it'll work. So let's go through this. First we got our data. Then we had our model, in this case the Reagan model, and then we have the VIF numbers and the tolerance numbers. All right, and then we had the correlation coefficient. Now what are we doing over here? Well, we're going to use another procedure that's not the LM procedure, but it's based on the linear models procedure, the LM procedure. It's called lm.ridge, and that's in the MASS package. Okay? So lm.ridge, and rather than type out lm.ridge and the model and the whole thing with it every time, I'm just going to say, call that x. So I just have x equals lm.ridge and then the model. Now notice that the model statement is just like the original model statement. Look what we had, Reagan model, lm, but instead of lm we have LM ridge. Otherwise, it's the same. You have ray field 3 equals the variables and so on like that. So here you have ray field 3 is modeled as, not equals, but is modeled as income, age, the regular variables and so on. And again, you have the data set, my data. The only thing that's really different is this lambda thing. What the heck is that lambda thing? All right, that's the only difference between LM ridge and LM. There's a lambda thing at the end of it. What is that? Okay, so to remind you, we covered something called the variance-covariance matrix. Now, we also covered something different, but that was very, very closely related, called the coefficient variance-covariance matrix. But I'm not talking about that now. The coefficient variance-covariance matrix was useful for understanding where the standard errors came from for the parameters and so on. But now I'm going back to the original variance-covariance matrix. So if you remember, the variance-covariance matrix has elements in it that have diagonal numbers, and these diagonal numbers are and I'm going to do a couple here. And I'll do one more. And it goes down, of course, until you have the summation here of xn minus x bar n squared. So the diagonal elements are, of course, the variances. So what you're dealing is you're taking the variable itself, x1, subtracting its mean, squaring it, adding them up. Next variable, dot, 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 all the way down the diagonals. Okay? Well, in the off diagonals, you have the covariances. And the covariances are when you're having your summing up again, but instead of going x1 minus its mean squared, you're going toward times the other variables. So you're having, oh, that's a 2. You're having the summation of x1 minus its mean times x2 minus its mean. So these things, and I'm not going to write these in, but because these ones vary, they differ for each one of these spots because you're having a different combination of variables. And of course, these things are reflective over here. So the top part of the diagonal is same as the lower part of the diagonal. But these things, covariances, are the things that go over here. Okay, for all the different variables. And the thing about that is this variance-covariance matrix is actually used in the formula, which you'll get derived. It's a very simple derivation. You'll get derived. It's in the formula for calculating what the slopes are. So if you have your equation here, y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 dot 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 so on in an error term. Well, the actual equation for getting you that vector of betas, so you have your intercept and all of your slopes, actually has that guy in it. Okay, does everything make sense? Now, the trouble is this. Sometimes there's a lot of multicollinearity. We want our x variables to have a lot of variance. You want the x variables to go up and they want them to go down. They want them to go all over the place. Why? Because then you can see if there's variation in the y variables that's being caused by variation in the x variables. So they have to vary in order to be able to see if they're varying together, the y and the x. So you actually want these variances here along the diagonal to be big. Everyone understand? You want the nice fat variation. You want income to go from really poor people to really rich people. So you can see if there's a lot of variation in income, is party ID changing, or is feelings towards Carter changing? You don't want everybody to have the exact same income. You want there to be variation. So these diagonal numbers you want to be big. But it's these off diagonal numbers that are causing the problem. You see, what if income is varying with education? Hey, people who have higher levels of education have more income. They have better jobs, stuff like that. So if income and education are varying together, then the covariance in the off-diagonal areas is going to be high. And then imagine yourself, put yourself in the position of being a computer program, R, trying to figure out what's the right slope for income and what's the right slope for education if they're both varying exactly the same. Imagine, put yourself in the head of a computer and saying, the guys asked me to figure out what the slope is for education and income, but they're varying in the same way. The rich people also have high education and the poor people have low education. What am I supposed to do? That means that the covariants are big. So what you'd like in a perfect world is for these guys in the off diagonals to be small and these guys in the diagonals to be big. Does that make sense, everybody? Should be really intuitive. Well, multicollinearity happens when the off-diagonal elements are too big. The correlations between the x variables are too close. So somebody came up with this very clever idea. Talk about a mechanistic way, but it was a moment of genius. Somebody was actually, in the history of ridge regression, it's very interesting to go through. Somebody was actually looking at this thing and looking at their model and say, damn, if I could only get it, yeah, if I could. The problem is that these ones in the middle on the diagonal aren't big enough relative to these guys. I wonder if I could just jimmy it a little. Why not just make them a little bigger? So somebody came up with the clever idea of multiplying the diagonal elements by a small number bigger than 1. For example, 1.0002. Do you get the idea? Where this 2, sometimes they refer to this as d, sometimes they refer to it as lambda. More often it's called lambda, but sometimes you see it called a d. This is the little guy, so it's 1 plus. So what you're doing is, if you multiply this guy here, this diagonal elements, by a small number bigger than 1, like 1.00 something, you're going to be inflating the diagonal elements relative to the off-diagonal elements. Mazel tov. It's done. The multicollinearity goes away. Literally, it goes away. It like evaporates. It goes away. And some people said, this is great. So you can get rid of the multicollinearity by doing that. The trouble is, you no longer have your original estimates anymore. You no longer have the original data. You can't fool Mother Nature. You've jimmied the system. And you maybe made your multicollinearity evaporate, but you have another problem. You no longer have blue estimates, best linear unbiased estimates. So remember William Tell out there shooting that arrow right over and trying to hit the apple on the sun's head? He does not want a bent arrow. He wants an arrow that's straight so that it hits the apple and not a sun. So you jimmied it, so you no longer have a straight arrow. Well, the question is, how bad is it? Now, if you're actually looking for the estimates, ridge regression, where you actually inflate the diagonal elements a bit, is not a good idea because you have a bent arrow. The question is, I got rid of the multicollinearity by inflating the diagonal elements a little bit. The question is, did I have to inflate them much? Now, if the estimates are not stable, it's exactly comparable to balancing on your tiptoes like this, okay? Now, if you're balancing on your tiptoes, a little nudge, boom, and you fall over. That means a little bit of bias on the diagonal elements, and whoosh, those estimates which you do have are no longer there. I mean, they're like blasted out of the universe. The new estimates you get have a different sign, way different magnitude. They go somewhere else completely. That means the original estimates weren't at all very good. But what if you're like this? What if you're stable on 2 feet and you tap yourself? Nothing happens. Then you tap yourself harder. Boom. Nothing happens. Then you have somebody hit you on the shoulder. Boom. You're still standing like a rock. Hey, you were standing steady to begin with. So that's comparable to increasing the amount of bias on the diagonal elements more and more and more, and looking to see at what happens to the estimates. If they stay still, you didn't have a problem. They were stable. If they don't stay still and they run like hell somewhere else, you had a problem. So ridge regression is really great from a diagnostic perspective. You see, the tolerance and the variance inflation index, variance inflation factor, will tell you if there's a lot of multicollinearity, but they will not tell you if there's a problem. There's a multicollinearity issue, yes, but does it cause a problem? Are the estimates wrong? They don't tell you that. The ridge estimates will tell you if there's a problem, if they're stable. And they are so easy to do, and so few people use them, and it's edgy. It's cutting edge, it's edgy. So if you use them, it's so easy to do, it's like, why not? You both learn a lot about regression, and at the same time, you demonstrate to people that you know more than just the basics. It's cool. So let's take a look. So what this does is, you get the LM ridge procedure, and this lambda, you see this thing? That's simply telling you, they scale it, but that's simply telling you how much bias to add. And they say, they start out with a little, and then a little more, a little more, and a little more, and a little more, and they see what happens to the estimates as you go, as you add more bias. And you just look to see. Okay? And then we want to plot it. Hey, we might as well look at it. Let's take a look. And we put a nice title on it, and then I'm having two little lines that I just put in there to divide up things. And then when I just type the letter X, it prints out the actual estimates. So now let's look at the output. The first thing we want to look at is the actual OLS estimate, ordinary least squares estimates. We had income of negative 0.15 for the slope. We have age of 0.23 for the slope. Party ID, negative 1.75. So the question we have is, we looked at the variance inflation factors and we looked at the tolerance, and it does indeed it looks like we do have multicollinearity going on in the model. The question is it a problem? Meaning, is this number, negative 0.15, very useful to us? Is this number, age, 0.23, is that a good number? There is multicollinearity, but is there a problem? Okay? So, I hate to use this example, it's such an awful one, but it's a little bit like saying you have a blood test come back and there may be a problem, so go in for a biopsy. The biopsy tells you the problem. The blood test is sort of signifying that there might be a problem. So the TOL and the VIF is sort of like the blood test. The ridge regression is like the biopsy. Sort of weird, but it sort of makes sense. All right, so let's now look at what happens. Just remember these numbers for income, age, and party ID. Negative 0.15, 0.23, and negative 1.75. You don't have to remember the others, just as a matter of principle. Let's go down and take a look at the ridge estimates. So these are the ridge estimates. Look at the first, now this is as you go down, and so they're increasing the lambda, or increasing the amount of bias. Look at the very first one. The first one for income. That was the same as the ordinary least squares estimate. Does everyone remember that one? Negative 0.15. Remember the one for age? 0.23? So the first one was the same as we got with ordinary least squares. Party ID, negative 1.75. And the same is true of all the other variables. The first number that you get back is the same as the one you got out of the LM procedure from ordinary least squares. Now let's start adding bias to the diagonal of the covariance and then recalculating the slopes. Look what happens. The smallest amount of bias, the very first estimate for the ridge regressions. What happened to income? Listen, folks, it flips in sign and magnitude. It goes from a negative 0.15 to a positive 0.11. Now you are going to actually end up saying a negative value for income, for Reagan feelings. That means as you got richer, you felt worse towards Reagan. Now does that make sense? Reagan was the Republican candidate. It doesn't make sense that richer people would have been less favorable to Reagan. richer people should have been more favorable to Reagan. So the negative 0.15 just didn't make sense. We add a little bit of bias, get rid of the multicollinearity, and what happens? Wow! The sign changes. That's the big thing, if the sign changes. And it changed right away. It didn't like took a lot of bias to do that. It like immediately flipped. So this estimate, negative 0.15, was not believable, and the problem was multicollinearity. Does that mean you want to use the positive 0.11? No. You don't actually use the ridge estimates for anything other than to find out that there was a problem. You don't say that the real slope was 0.11. You get rid of the multicollinearity other ways, like dropping variables or using a procedure called the centering procedure, which I'll explain in a little bit. I wrote a book, actually a dissertation, on the centering procedure. They talk a little bit about it in our textbook, which is very useful. But the basic idea here is that that variable, the estimate for income, is not believable. Let's look at age. The original OLS estimate was 0.23. What was the next if you add a little bias? 0.24. Huh? It didn't even change. It was like the same. Let's add more bias. Wow, we're back to 2.3. Let's go all the way down. We're 2. Look at, you add a ton of bias. When you get down here, beyond like 4 or 5 or 6 of these things, you're adding a lot of bias. I mean, you don't need to get down to the 27s. Just if you get down to the first few, the number is not changing, period. It's not flipping in sign for age, and it's not flipping in magnitude. It's not going like from a big positive number to a big negative number. It's got approximately the same magnitude and the same sign. What does that tell you? You can bash the heck out of this variance-covariance matrix by increasing the diagonal, and it's not going to make a difference. That slope was stable to begin with. You can believe that one. That 0.23 was a good one. Okay. Ask me a question. Is it okay? Okay, let's look at some of the other ones. What about party ID? Party ID goes from strong Democrat to strong Republican. So this is Rayfield 3. So this is saying that as you became more Republican, your feelings towards Reagan went down. That was that negative 1.75. That's what that's saying. Is that a believable thing? On a conceptual basis, does that make sense? I mean, if you're more Republican, you're going to be more happy with Reagan, right? So that negative 1.75 just doesn't make sense conceptually. What happens when you add a little bias in the ridge regressions? Look at that. Immediately the magnitude starts dropping, and on the 4th iteration, with just a little bit of bias, you flipped in sign. And then it starts growing in the positive direction. So that negative 1.75 was a problem. It was not believable. And multicollinearity was the culprit. Are we okay? I mean, it's real simple to do and real simple to interpret. And then I'll show you the plots. The plots are to die for. Okay, so let's go through this real quickly. This is how fast you can use the ridge estimates. Income, is that a problem? Yep. That number wasn't believable. What about age? Nope. Age was good. Party ID. Ooh, that was a train wreck. Can't believe party ID number. Rep Part 3. Feelings towards the Republican Party. That's pretty stable. Look at that. That's solid. That's good. Okay. The multiplication of income times age. Well, it looks solid. The same sign. Look at the same sign and the same magnitude going all the way down. Okay? All right, so now let's look at some of the other. Look at that. They do a lot. These ones near bottom, near 100, you don't need to go anywhere near those ones. It's the first 10 that you really see the difference. If you don't see a major change in the first 10, then it's okay. Okay, what about this one? What about income times party ID? Well, look what happens. You don't change in sign, but the magnitude drops almost immediately from 0.21 down to close to 0. So that probably wasn't so good. What about income times feelings towards the Republican Party? It goes pretty close to 0. You didn't have much to start with. Maybe, maybe not. Okay, what about party ID here? It looks like at times feelings towards the Republican Party. Looks like the magnitude almost completely drops away. And then that last interaction term, well, it's really so small to begin with. I'm not really so sure if it's useful to us, okay? So the idea is that the ridge regressions will tell you which ones there's really a problem with. Now let's look at the plots. Now these plots are actually scaled. So if you actually try to look for these numbers in the ridge regression estimates in those plots, you won't be able to find them. Because these are the actual numbers scaled to look like the OLS numbers, but the plot is not. So if you actually try to look for the 0.21 for income times party ID, you won't find it in that plot. This has been scaled so that they all sort of have a similar type of range. If you wanted to see what the actual stuff was, you can, I'm going to do it for you, but you actually don't need to do it. There's a command you can type called head x, and that tells you everything in it. And that, in fact, tells you what the scales are that they use to scale those numbers so that the plots look sort of nice, okay? So if you divide those scales into the numbers that you get above here, you get the same numbers as what you get in plotting and so on. Anyway, so let's look at these. But nonetheless, you can figure out which one's which by simply looking at which ones change dramatically and then in terms of sign. So all you have to do is say what one starts like really negative and then immediately goes positive. So this one here goes from really negative and immediately goes positive. This one goes from negative to positive, but there's not much of a change. This one has a big change. So this is probably, you can figure out by that which one's which. This looks like it's income. So, and so on. But anyway, these are the plots that you can look at to sort of see how these estimates are going. Basically, what you're looking for is a plot, not necessarily to follow the individual lines, because you can follow the actual variables as they're moving themselves, as the coefficients are varying themselves. You can actually follow that easier in the table that was above, that we previously looked at. The plot is useful as sort of a Rorschach test. If you just look at the plot, you can sort of say, this model had problems. What do you look at when you see this plot? What do you see? You see some variables, some coefficients that are losing all of their magnitude, others are flipping in sign. You see how they're flipping in sign? They're going from a negative to a positive. And this one's losing magnitude, it's starting here and going to there. That's a huge drop. We have one here and going here. So it shows you that this model has multicollinearity problems. I mean, it really does. It not only has multicollinearity, but the coefficients really aren't so good. Okay? You see this vertical movement. What you'd really like to have is lines going from the left to the right without much vertical movement. You'd like to have a lot of lines that are just going that way, but not going vertically up and down very much. So the plot is very useful just as a Rorschach test for the actual model to see if everything is okay. You can just look at the plot, and if most of the lines are just going horizontally without them crossing the zero, then you're okay. And so this is one of those beautiful plots that's great to have in your PowerPoint presentation that you don't normally show the people, but if somebody in the room says, well, I think you have some interaction terms in there, so I don't think I'm going to believe your estimates because you must have multicollinearity. You can throw this as one of your reserved PowerPoint plots up and say, no, we don't. I've checked it with ridge estimates. Those estimates are solid. With small amounts of bias, those estimates are not moving anywhere. Here's the plot. See the horizontal movement on that stuff. The person will shut up. Do you get the idea? It's a very useful diagnostic. And it's very rarely used. It's edgy, cutting edge, but it's easy to do and easy to understand. I don't know why it's not taught more often. When I was taking graduate level econometrics classes in an economics department at Washington University, they covered this. I mean, it was a useful thing. But I have very rarely seen other people cover it. So, it's something, and if you look at the internet of people doing ridge regressions, they're wondering about how to use the ridge regressions to actually use the numbers. They want to actually get the ridge regressions and add a little bias and actually use the numbers as a slope. No, you don't go there. Those numbers have bias in them. You don't go there. You don't ever want a number that has bias. You want to know is the number that you do have with an unbiased estimate, is it good enough to work with? And this ridge regression tells you if it's good enough to work with. Everyone okay with that? Now, how can you deal with multicollinearity? So we've covered how to diagnose it with the variance inflation factors, tolerance numbers, and we've also covered it with regard to the correlation matrix. We've also then said, all right, that's equivalent to the blood test. What about the biopsy? Is there really a problem there? That's the ridge regressions. So the ridge regression tells you it's stable. Is there a way to fix it if you do have a problem? There is the standard approach. The standard approach for fixing this is to eliminate that which offends. To eliminate that which offends. So you look for the variables that are more closely correlated with the other variables that you don't really have a lot to talk about and get rid of them out of the equation. Just delete them. Don't include them in the model. And then you check it again and you look if your estimates are stable. And if you're stable, then you're done. Great, it's finished, it's over. On the other hand, there are some other tricks to do it. So the dominant one is to just simply eliminate the variables. There are other ways to do it. Some of them are really fancy, such as principal components. Let me just sort of mention principal components. I don't find it to be a very useful thing. It's related to factor analysis. But the basic idea is you have a data matrix that has, say, 5 variables in it. Well, you're supposed to have 5 dimensions. But the correlations between the variables are so high, you know, it's almost like you have 4 point something dimensions. You don't really have the full 5. And our program can't tell the difference between some of the variables. So one of the things you can do with principal components is to take the elements out of all the different variables so that you end up with like 4 orthogonal dimensions. You literally get rid of one of the variables by having these 4 other variables. The trouble is that these other variables that you're creating, these principal components, they don't really represent anything. They're like a mathematical creation. And so then you try to figure out, well, what does these components, what do they actually mean? And you look for what their correlation is between that and the original data. So that's messy. It's not easily interpretable. And you really wonder if you're dealing with anything that's real, in my view. So I don't like doing principal component estimation to get rid of multicollinearity. I think your best strategy for doing this is one of 2 things. The first thing is to eliminate the variable that offends. That's actually the easiest and the one you should do. There is another one called the centering procedure, which is really cool. And it's not taught very often. It is mentioned in the book, but I guess because I wrote a book about it, I like it. But to be quite honest, very few people do it. So let me show you where it is and then basically describe it. And you'll see how easy it is to do. And in fact, it's very useful, and you can actually keep the same variables and actually get your estimates from it. But it's, again, not often done. So you're probably going to be left with the original procedure to just simply eliminate the variable that offends. The only reason I'm mentioning the centering procedure is that sometimes you're going to get a model where there's a lot of multicollinearity and you found out there is a problem and you don't want to get rid of all the variables. There's every single one of the variables you want in there for some reason. And if that happens, I always have a plan B. And this is my plan B. Okay. In your books, you'll find it explained starting on page 343 and going to 344. Now, the centering procedure is very useful if you have just a few interaction terms. If you have just a few interaction terms, not the kitchen sink like we were doing, where we were multiplying everything by everything just in order to get multicollinearity. If you have just 1 or 2 interaction terms, and just by chance it turns out that your diagnostics for multicollinearity indicate you have a problem, well, you don't really have much to eliminate. You wanted the interaction terms that you have in there so you could talk about them, so what do you do? So on this page, 343 and 344. And this gives you an indication. Here, I wrote a book about this subject, and they have 2 pages on it. Do you get the idea? That's how much it's actually used. So I think this is an underexploited, they don't even talk about ridge regression, but this is an underexploited aspect as well, this idea of the centering procedure. Now the centering procedure is very useful, and I'll use one of their examples that they have here. Where we have their y equals, I'm just going to use my notation, and then I'll explain it. Here we have 2 variables, x1 and x2. And we have the variable originally as they are, x1 and x2, but we also have the interaction, the multiplication of x1 and x2. And we have a theoretical reason for why that should be there. So we want to keep the interaction term. So the mechanics of doing the centering procedure is actually really simple. What you actually end up doing is rescaling, it's recentering the variables around their mean. So really what you're doing is you're going to have y, and I'm going to have to switch here to alpha. So we have alpha 1 plus, alpha naught plus alpha 1 plus alpha 2, that'll be x2 minus x2 mean, okay, and then alpha 3, and that'll be x3 minus x3 mean, plus dot 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 the error term and so on like that. So let's actually look at what the book has. So anyway, those of you who have the book, it's on page 344. And basically what you're actually doing is you're taking every variable and you're subtracting the mean for that variable from the actual values and creating a new variable. Now, the practical results of doing this is that when you do this, you find out 2 things. If you were to have your original model look just like this, without the interaction term, and then you add the interaction term, you often find that these estimates, beta 1 and beta 2, that they change. Meaning they're different because things are being caught up in the interaction term, and you're wondering if the multicollinearity was the issue. If you do the centering procedure, where you subtract each variable from its mean, you get back the same estimates, the original estimates, that you would have gotten without adding the interaction term. So your alpha 1 actually turns out to be very similar to the beta 1 in the model without the interaction term. And your alpha 2 turns out to be very similar to the beta 2, again in a model without it. And then your interaction term turns out to be something that's reasonable. So you end up getting back your original estimates and a more believable understanding of that estimate. And mechanically, for the interaction term, oh actually this one I didn't write correctly, so this is x1 minus x1 bar times x2 minus x2 bar. Sorry about that. So that's the interaction term, okay? So you're multiplying that variable minus its mean times this variable minus its mean, and so you get a little bit more stable estimates. Reading from the book, just so you get an idea. The estimate for the interaction, and they actually show, I wish I could show you with the document camera, they actually have this done with real numbers, and they have an example. They show you an example with the interaction term and without the interaction term and how you get back the exact same numbers. So the estimate for the interaction term is the same as for the model with the uncentered predictors, meaning this guy here, A3, turns out to be the same as what you get over here if you have the full model without centering, including the interaction term. Now, though, the estimates and the standard errors for the effects of x1 and x alone are similar to the values for the no interaction model. So now this guy and this guy are the same as beta 1 and beta 2 without the interaction term. Now you have these guys looking like the original without the interaction term, and with the centered version, this guy looks like that guy with the full model with the interaction term. So you get your cake and you get to eat it too. And the multicollinearity is much, much, much less. This happens because the coefficient for a variable represents its effect at the mean of the other variable. Does everyone listen to that? This happens because the coefficient for a variable represents its effect at the mean of the other variable, which is typically similar to the effect for the no interaction model. Okay? Also, the statistical significance of x1 and x2 is similar as in the no interaction model. So, this is plan B. Plan A, get rid of that which offends. Plan B, if you can't get rid of it and you have an interaction term that you really want to talk about, but it is causing problems, the centering procedure works. And you now know a nice place to read about it. And if you want to read a whole book about it, there's my dissertation. But other than that, you can just read those 2 pages, and he gives a couple citations there, which is actually very useful. It's a real sort of magic trick out of a box type of a thing. So it's very rarely done, but it's extremely useful for certain cases where you actually need it. Okay? All right, how are we doing for understanding multiple regression with multicollinearity issues? Because we basically covered that. We're done now.